We're going to continue our work with probability in Chapter 5. We're going to start talking about probability distributions. Probability distribution discusses the probabilities of various events. So kind of a fun one to talk about is the sum of two dice. When you roll them, you can get any number between 2 and 12. The probability distribution would be the P of X here that describes the probability of these various events. So just kind of a quick rundown here. You don't have to copy it down yet. We'll put it in our Google Sheets later. The probability of rolling a 2, snake eyes, is 1 in 36. Then probability of a 3 is 2 in 36. Like I said, you might want to copy these down later, not now. 3 in 36, 4 in 36, 5 in 36, 6 in 36, and then back down, 5 in 36, 4 in 36, 3 in 36. I think you can kind of get the pattern here. 36 and 1 in 36. So this is a probability distribution because it describes the probability of each event in this experiment. Now, there's going to be a couple things that we're going to expect and want out of our probability distribution. So for a probability distribution, requirements. There's two. So the first one is that all these individual probabilities have to be valid probabilities. Now, probabilities range between what and what? What are the two extremes for probabilities? 0 and 1. Thank you. So the first requirement is that all of our probabilities have to be less than or equal to 1 and greater than or equal to 0. The second thing is that the total of these has to equal 1. Basically, if you add up all the probabilities, something has to happen with certainty. So the notation here is the sum of P of X equals 1. So those are your two requirements. I guess there's kind of another implied requirement here, and that is you have a number here for X, your random variable, as opposed to something that you would see in problem number 10. Instead of a number there, they've got some descriptions of various things that can happen. So this goes back to the Microsoft Instant Messaging survey about the best way to flirt. The author doesn't like this as a probability distribution because these aren't numbers. And we can't do the kinds of calculations that we would like to with this distribution because these aren't numbers. So let's turn our attention to something different then. Problem number 8. Let's take a look at that one. And we're going to plug that into our Google Sheets. So let me clear this out. New spreadsheet. There. So in the first column, let's put all the different things that can happen in terms of the random variables. This is male color blindness. It says when conducting a research on blindness in males, color blindness in males, a researcher forms random groups with 5 males in each group. The random variable X is the number of males in the group who have a form of color blindness based on data from the National Institutes of Health. All right, so if you have 5 people, 5 men, then the number of males that could have color blindness could be 0, 1, 2, 3, 4, and 5. The associated probabilities then are given in that table. So they're giving us what we want to check out as a probability distribution. So 0.659, 0.287, 0.050, 0.004, 0.001, and they have 0 plus. It's some positive probability, but it's pretty small. So as far as deciding is this a probability distribution, well, it meets the first requirement, right? That all the probabilities individually are between 0 and 1. The other question then is, do these add up to 1? Well, let's not do it manually. Let's let Google Sheets do it for us. So equals, and then sum. And let's just select all our data up here. And it sums to 1.001. So technically it's not a probability distribution, but what I think is happening here is that you've got some rounding error. So it's meant to be a probability distribution, it's just that there's a little bit of rounding error. So we'll tolerate that. Let's clear this out and then, let's see. Yeah, let's work with, let's go back to our dice example. So I'm going to clear this out, I'm going to select it, and then edit, and just delete rows 1 through 7. Let's go back and enter our dice example. So things that can happen when you're rolling 2 dice. So let's take a quick look back here. These are our events. You can get rolls of 2 through 12. So I'm going to enter those, and I'm going to work on getting in our probabilities as well. So 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Now the probabilities were 1 out of 36. Well, it's not. Tell you what, let's do it a little bit easier. Let's see. I'm just going to work with the numerators. 1, 2, 3, 4, 4, 5, 6, and then 5, 4, 3, 2, 1. Now these aren't probabilities yet. I'm going to turn them into probabilities by dividing them by 36. So once you have the numerator put in, let's do this, equals this number divided by 36. And it should give me a nice decimal value. There we go. So once again, divide by 36. If you have that first operation typed in, then you can copy it down to all the rest. So select it and copy it, and you should get something that looks like this. Now I'm going to try and clean it up a little bit here by decreasing the decimal places a little bit. Oops, why don't you do decrease as well? Yeah, I don't need to see a gazillion decimal places there. All right, so here's your probabilities. If I was to sum this up, equals the sum of this distribution, then the sum of that should be 1. Yes, good. So a little bit better than problem number 8. But what I want to move to next is working on a calculation called the expected value, or the mean. So the mean is got kind of the same meaning here as what you're used to from our work in the previous few chapters. That is, the mean is what happens on average. So the difference is we're going to start calling that the expected value sometimes. So the mean, or the expected value, which is your mean, is going to come from this calculation. It's going to be the sum of x times p of x. And that's going to be the mean. Now what we're used to as far as notation is calling the mean x bar. We're not going to use x bar to denote the mean here. X bar is the sample mean. And we've got all the possibilities that can happen. This is our entire population of things that can happen when you roll dice. So instead of using notation for the sample mean, we're going to use notation for the population mean. So this is a Greek letter. It's called mu. If you want a better look at that, you can type the letter M when using the symbol font, or better yet, just look in the book. So we want to calculate the average value. What's happening on average when you roll a pair of dice? So let's look at that. I need to calculate a column of x times p of x, and I need to add that up. So let's go back here to our sheets. In this column, I want x, which is in column A. These are the different things that can happen, times the probabilities. So I suppose I can just hide that there, make it a little bit more clear. We want to work with these two columns, x and p of x. So in this next column, I can type equals this times, and that's just the asterisk, and what I have in this column. So x times p of x. Mira? No? Okay. Let's do that for all of our data, or all of our random values. So copy that, Control C or Command C if you're a Mac user. And let's paste that all the way down here. So these are your values, x times p of x. What I want next is the sum of these values. And that's going to tell me, on average, what are you going to roll with a pair of dice? What's the average roll? So let's sum that up. And I want to see what you guys got. So let me walk around and see how you're doing on this. So sum that up and let me know what you're getting. Yes. Perfect. It should be a nice even round number. Okay, so my brief sample seems to suggest that you guys are doing all right. So the sum from 1 to 11 of all these values should be exactly 7. So 7 is your average roll. If you're rolling dice all night, then on average you'd be getting a 7. Does that guarantee that you're going to get a 7 on any particular roll? No, it just says that's what's going to happen on average. What happens on any particular roll can be anything. So it just kind of depends on luck. But your average roll is going to be a 7. Now let's take a look at a couple other expected values here. I've done expected values for a couple games that you would run into, say, I don't know, in Vegas or even in Detroit. So in a roulette, game of roulette, there's 38 numbers, numbers 1 through 36, 0, and 00. If you bet $5 that your number is going to come up, there's a 37 out of 38 chance that you're going to lose that $5 bet. If you win $175. Hey, not bad. But let's calculate the expected value of playing this game. So if you multiply x times the probability and add these up, we get a negative 0.26. Likewise, you can calculate the expected value for playing craps, putting some money on the pass line, probability of winning, probability of losing, and again, you can calculate an expected value. What I want to ask you about, though, is that negative. What's that negative saying here about your expected value for these games? Yeah, you're going to lose money. On average, you're going to lose money is what this is saying. So, given the choice, which game would you rather play? The first one, roulette, or the second one, dice? Dice, because your expected value is not as bad. Okay, and my point to you is that when you're playing games of chance, you want to try and minimize that expected value. You want to make it, if it's negative, you want to make it as minimal as possible. All right, we're going to continue with this. Our expected value, that's your mean, but we can also calculate a standard deviation from this and start trying to figure out, well, what's your typical values and what's your atypical values when you're playing some game of chance or when you're just looking at events on a probability distribution. So let's keep working with, you know what, let's do maybe an easier data set and then we'll go back and work the slightly harder one. Let's take a look at problem number 20. Which gives us a data set, says, it describes the results of roadworthiness test on Ford Focus cars that are 3 years old. The random variable X represents the number of cars that failed amongst the 6 that were tested for roadworthiness. So, the possible number of failures, if you're testing 6 cars, and I wouldn't clear this out yet, might go back to this, but the possible number of failures would be 0, 1, 2, 3, 4, 5, and 6. Let's put in those associated probabilities. So the probabilities, and these are in the book, are 0.377, 0.399, 399, 0.176, 0.041, 0.005, and the last two are really small. They're positive probabilities, but up to 3 significant digits, they round down to 0. So those are our probabilities. Let me see if I can't make this a little bit bigger for those of you towards the back. There you go. So the first thing I want to do is I want to calculate the mean, the average number of cars that you're going to see with that aren't roadworthy. So to calculate that, remember it's going to be our column of x times p of x. Let me label that here, x here, and then, whoops, didn't want that. P of x here. Nice if those were right justified, but oh well. All right, so the next column over here then that I want is x times p of x. So x times p of x. I'll put that in this column. So I'll take equals this times this. And then I'll copy that calculation all the way down. The expected value then, my mean, expected value, is going to be the sum of this column. So what are you guys getting for the sum? 0.894. All right, perfect. I'm getting the same thing. So on average, you expect a little bit less than one car to not be roadworthy. Okay, but now we need to find the standard deviation so we can start figuring out what's typical and what's atypical. So that standard deviation is another calculation. Let's go through that. And let me cut back to, whoops, wrong one. Here. Let's figure out how to calculate the standard deviation. We're going to start with the variance. Do you remember the relationship between the variance and the standard deviation? All right, one was the square of the other. The variance is the square of the standard deviation. So the variance is going to equal the sum. Oops, thank you. The sum of x minus the mean squared times p of x. Now you're kind of lucky in statistics, you don't have to memorize these formulas. Any formula that you're going to need in this course, I will give to you. So it's not something you have to have memorized. Kind of like what we did for our mean, we're not going to use s squared anymore because s refers to the sample variance, or s squared refers to sample variance. We're going to use the population parameter. We're talking about the population of all values here. So that's going to be a sigma. And in our case here, because it's the variance, it's going to be sigma squared. Standard deviation is just going to be the square root of that. So standard deviation is going to be sigma equals the square root of the sum of x minus mu squared times p of x. My expectation is it's going to be a lot nicer to do this in Google Sheets than it is to do it by hand. So take a look at that. Let's go back to Google Sheets and see if we can't crank out this calculation. Figure out first what the variance is, and then take the square root of that to get the standard deviation. All right, so over to here. Let me close that out. There. So for each of these, I want to take my column of x and subtract off the mean, and then square it, then multiply by the standard deviation. Do you want to do this in 2 steps, or do you want to do it in 1? Doesn't matter to me. One big step. All right. So that one big step is going to need to look like this. I want to take x minus, I'm going to just type it in as mu squared times p of x. So that's the column I need to do here. So let's see if we can't accomplish that. So it's going to be equals, parenthesis, my x is in column A, so let me click on that 0, minus the mean. Now you've got 2 choices for the mean. You can just type in 0.894 and that's fine. Or, some people call it laziness. I prefer to think of it as economy of movement. All right, I'll just click down here, which is where your mean is, and that's better because it's a nice exact value. You're not always going to get the exact value if you just take the first few decimal places. I need to square this. How do you square it? You hit the shift key and then the 6. That little up arrow gives you, the ability to do a power. So I want that to the 2nd power. Last but not least, I need to multiply that by p of x. So times p of x. Now it's going to be kind of a disappointment here because this first calculation, you know what? No, it's not necessarily going to give us a 0, is it? No, it doesn't. From here, I want to copy that all the way down. Now the total of this column is going to be the variance. So that's going to be the sum of all of these values. Okay. So variance of about 1.85. Let's get the standard deviation then. So our standard deviation is going to be the square root of this. I'm pretty sure there's a square root function. The nice thing about Google Sheets and Excel, for that matter, is when you start typing in what you think might be the thing. So SQ, and there you go, square root. So SQRT, click on the previous cell. The square root is 1.36. I'm not sure I'm trusting this. Let's see. Oh, okay. All right, tell you what, let's go back and let's just type in the mean, 0.894. And let's copy that. Yeah, the dollar sign is a kind of a cool trick, although I'm not sure I want to turn this into a class about really getting that nitty-gritty with Excel. It's a nice trick, though. Thanks. All right, so I guess my advice then would be to just subtract off, just type in the first few digits of the mean. I'm not liking that, but I guess that's what we're going to have to do. And this looks a little bit more like what I expected. So the standard deviation here is about 0.9. And the expected value was similar. It's about 0.9. If you look at the book carefully, the author suggests that you round things to one more digit that's in your data. So we would round the expected value to 0.9, and we'd round the standard deviation to 0.9. So let me just repeat this calculation one more time, just to make sure that everyone's had a chance to keep up with it. So equals x is in column A, minus, and we're just going to type in the mean for right now, 0.894 squared, so up arrow and then a 2, times, so shift and then 8, and then p of x. And then you should be able to copy that all the way down and sum up to get the variance, square root to get the standard deviation. How many of you got the variance correct, or the standard deviation correct? Get all the way down there. All right. Dom, need a little help on this one? All right. I'll tell you what. Let me finish this one. We're going to do another one, and then maybe we can try and keep up with the next one. If you're still struggling, I'll definitely come back and help out. So just like before, we want to know what's the typical values. What was it that defined the typical values for us before? What defined our typical values? You just did it on your test. Yeah, within 2 standard deviations. So that's going to be what's typical. So let's try and understand what's typical for this data set. So the mean rounds to about 0.9, and the standard deviation also rounds to about 0.9. Our typical values are going to be mu minus 2 sigma to mu plus 2 sigma. So in our case, 0.9 minus 2 times 0.9 to 0.9 plus 2 times 0.9. So negative 0.9 to 2.7. So on the one end, our typical values encompass 0. So it's not unusual to get 0. And on the other end, it goes up to 2.7. So what's that saying about our data set? What would be the unusual events to see? Yeah. Now, can you get 2.7 cars that failed to be roadworthy? No. So where it's going to have to start is at a 3. So to get 3, 4, 5, or 6 cars that are not roadworthy, those would be your unusual observations. But what's typical is probably something close to 1. And the atypical is anything 3 or above. So your expected value is about 0.9. You can't get 0.9 cars to be roadworthy. It's either 1 or 2 or 0, etc. But on average, that's what you would expect if you're performing this experiment quite often. Let's go back to rolling dice and see what happens when we roll a pair of dice. So I think the last question in here is based on the results, is 3 an unusually high number of failures among 6 cars tested? The answer is yes, because 3 is in the unusual range. This is typical, and this is unusual. Okay. You know what? Let's do one more with a smaller set of numbers as opposed to going back to doing the craps one. Maybe I can leave that as a homework assignment or something like that. But I think what you'll find out in playing or rolling a pair of dice, the unusual values to get would be a 2 or a 12. Everything else is going to fall within 2 standard deviations of our mean. Let's take a look at problem number 14. So when betting on the pass line in the dice game of craps at the Mohegan Sun Casino in Connecticut, the table lists the probabilities for the number of bets that must be placed in order to have a win. So how long do you have to stay there before you get lucky and have a win? Well, let's put these values into our spreadsheet. So 1 through 5, and then these associated probabilities. I'll copy them as well. So let me switch over to here. I'm going to get rid of all of these. Actually, you know what? I guess I can use some of them. So, delete rows. And let's delete some values. Okay, so I guess I don't need the 1 or 0 anymore. It's 1, 2, 3, 4, 5. The probabilities are given. So let's type in those probabilities. Probability that you only need 1 is a 0.493. Roll before you get a win. And then a 0.250. So a 25% 25% chance you need 2 rolls before you see a win on the pass line. 0.127, 0.064, and 0.00 or 0.033. Now let's just check to make sure that this is a distribution. What would I need to check in order to make sure this is a distribution? Yeah, it has to add up. Well, all these individually have to be between 0 and 1, but the total has to be exactly 1. So equals, and let's see how good the author is and making sure that this, yeah, is it going to be a little short? Yeah, so not exactly a distribution, is it? Yeah, so I guess we're short a little bit. Let's assume that you get lucky on that 6th roll. So let's put in a 6 here, 0.033. I think that should do it now. Because I actually want to go through with this calculation. There we go. All right, so now this is a probability distribution. So add in that extra 1. That gives us a probability distribution. And let's figure out the expected value for this probability distribution. So to get that expected value, I want to take x times p of x. So let's type in an equals, and please try and stay with me. X times, and then p of x. Now let's copy that down for the rest of these. There. Now it's the sum of these that's going to give us our expected value, our mean. So on average, how long do you have to stay there before you're going to see a win? So that's going to be the sum of these 5, or these 6, I should say. So a little bit less than 2. And I'll pause here. If somebody's not able to keep up with this on their sheet, then let me know. Dom, how we doing? All right, good. Let's work on calculating the variance then. So this is your mean. Here's your variance, or well, here's part of the calculations for your variance. We want to take left parenthesis. No, wait, before we do that, we need an equals, and then left parenthesis, x minus mu. And I guess the lesson from the last one would be to just type in that value, the dollar sign. FN. It'll pin it there. I'm not sure I want to get that detailed with Google Sheets. Yeah, no, you're right. And I played around with the dollar signs, and they're pretty cool. They lock things. It's nice. What Dan's talking about is that there's a way to lock something in to your calculation with a dollar sign, but that's starting to get more into spreadsheets and less away from statistics. So let's just focus on this. 1.993 squared, and then times p of x. So p of x is in column C, or at least it is for me. Might be in column B for you. Once you've got that, press the enter key, and let's do that. Repeat that calculation for all of our. Oops. So copy, and let's repeat that calculation all the way down. And as before, I want to find that sum. That sum is going to be our variance. So that sum, can I cheat here and copy that over here? Yes. Equals sum. So we get a variance of about 1.7. The last thing to do is to do the standard deviation. And all I need to do now is take the square root, so SQRT, of my previous calculation. You guys getting different numbers?
I didn't get it the first time, and then I typed in the equation again, and then I got your number.
Let's just...
I just did it twice, and the second time I got the same one, but the first time, or the second time I got the right one.
Let's... let me just do it all over again. Let's just see if so equals left parenthesis x minus mu, which was 1.993. Then I want that squared times p of x. Now p of x is in that labeled column. So for me, it's column C. It might be a different column for you, depending on what you did. I hid column B for my convenience earlier. But there's your x minus mu squared times p of x. And that number didn't change, I don't think. If we copy these all the way down and paste it, let's see if this number here where our variance changes. No, it stays the same. So pretty confident that that calculation is correct. So we got a mean of 1.93 and a standard deviation of 1.3. So call it a mean of 2.0 and a standard deviation of 1.30. Now, if I wanted to, I can do my little range of mu minus 2 sigma and mu plus 2 sigma up here. I mean, the numbers are pretty straightforward, so I think I'll do them by hand on the notes here. So if I want mu minus 2 sigma to mu plus 2 sigma, it's going to be 2.0 minus 2 times 1.3 to 2.0 to 2 times 1.3. So it's going to be negative 0.6 to 4.6. So those would be your typical values. Let's be careful as we apply that to our particular problem. So we get a range of values from negative 0.6 to 4.6. What's that say the unusual values are for our particular distribution? Yeah. If you have to wait 5 or 6 rolls before you get a winner, then that's unusual. Those are outside of our typical values. Our typical values are going to be anything from 1 to 4. Those are going to be inside of that range that we just calculated. So, typical would include 1 to 4. Unusual is going to be 5 and 6. Okay, nice. Since this is most likely your first time seeing this, let me tell you, this is a lot more user-friendly than having to do all these calculations on a calculator. So it does work out kind of nice. Are you able to match these calculations? Okay. The other big thing that I wanted you to understand was just what the expected value means. It tells you what's going to happen on average. Now, when you're betting $5 on a roulette wheel, you're either going to lose $5 or win $175. How can you have an expected value of negative 0.26? Well, you can't. It's not an outcome that you're going to get from this experiment. What this reflects is, on average, if you've played this game all night, how much you're going to lose. If you've bet $1,000, then you're going to lose on average. So betting $1,000 would be 200 of these bets. So 200 times that, so what? $51.20 on average is what you'd be losing. But it's an average. It's not telling you what's going to happen on any particular event. And the negative there reflects, at least in these two examples, that you're going to lose money on average. Okay, for homework. Try 7 through 17. Seven through 17 in homework.